Hi everyone, welcome. And I'm not sure if this is the last video, but this will be the last recording I do for this semester, because I have finished all the lecture notes, and then I don't know, but I just want to finish recording everything. And then if the video turns out to be too long, then I might cut it into two, and then one for this Wednesday, one for next Monday. Okay, so the last section of this class, okay, I really wish we have more time to talk about this, but this is the last section, is that we will try to build a connection between the quantization of light, which we briefly discussed in the past 3 videos, and then we make that connection between the quantization of light using creation and annihilation operator, and then connect it to the nonlinearity, okay, we talked for the entire semester, and then see that, okay, if there's how can we write down nonlinear equations using quantum mechanics, and also how it actually predict something different than in the classical case. Now, so the first thing, okay, to make this connection, one thing we have to remind ourselves is the framework of quantum mechanics. Right, the framework of quantum mechanics is that you need to find the Hamiltonian. Right, you need to find the Hamiltonian so that you can apply Schrodinger equation or other equation, for example, in Heisenberg picture, the equation of motion. So that you have to start with Hamiltonian and then finish everything like this. Okay, and so this is criteria 1, and then criteria 2 is that there should be a way that you make the transition from quantum case to classical case, right? Because in quantum case, what we say is that we write the electrical field and magnetic field as an operator, right? So, but when the intensity of light is very large, right? When you don't see individual photons, there should be a way that you can convert it back. You're using the same equation, so the transition. Always say that whatever your equation is, it should be consistent. Or you can go to, let's see, you can return to classical equations. Yeah. So this is always a test for any new theory that you want to break away from. You want to break away from the classical physics, that you always have to show that, okay, you can come back. For example, the special relativity. Okay, in the special relativity, what you will see is, okay, if you take the limit that the velocity of your frame or velocity of your object is much smaller than the speed of light, then it returns to Newton physics. So this is kind of a very important test for all the new theories. Now, well, I will give an example here. We'll use the simplest example here is a Chi2 material, right? The Chi2, okay, the nonlinear process of Chi2. All these things are extremely similar, and especially in the quantum case, it's very easy to figure out. Okay, so in a Chi2 case, you have let's say just harmonic generation, right? There's 2 types of wave that would be in this crystal. It will be, let's see, we say E1 is the omega t, and then there's the E2 wave, right? It's a harmonic of that. Right, both of them, okay, in a crystal, and so in a very I want to give you guys the answer, okay, at the very beginning, okay, how can you write down the Hamiltonian in a very quick way? Okay, the intuitive the intuitive picture, okay, is a physics picture, is that in this process, there are, when you have two wave, okay, when you consider two wave in this Chi2 material, there are two processes that's happening. One is that harmonic generation, right? You have two photon that's from the omega frequency, and then degenerated a 2 h bar omega, the harmonic generation, the doubling the frequency. This is one process. Okay, the second process is the reverse process, right? You have 2 h bar omega, and then it's split into h bar omega, two photons of h bar omega, right? So if this process is dominating, then we say, in the classical way, we say that, okay, you're doing harmonic generation. Okay, if this process is dominating, then you can think about it. This is a special case of a difference frequency generation, right? 2 h bar omega minus h bar omega give you another h bar omega. This is sometimes called degenerate parametric amplification, or degenerate frequency difference generation, right? So depending on your condition, right? If your input is mainly omega frequency, then you primarily have harmonic generation. If your input is 2 h bar omega, and then you tune the phase matching condition, then this is primarily degenerate difference frequency generation. Okay, so the way to write down the Hamiltonian, okay, is that, let's see here. The way to write down Hamiltonian, okay, first is that we already know that first of all, okay, there are two waves, right? So for optical wave inside, well, let's assume it's inside a cavity, okay, just for simplicity. Inside a cavity, if it's inside a cavity, then when you write down the Hamiltonian, it's always h bar omega, for example, A1 dagger A1 plus 1/2. Right, this is the, this is the Hamiltonian of the omega frequency wave, right? When it's in a cavity, we know that this is Hamiltonian without any nonlinear interaction. And then, if you have this, then you have to write down the Hamiltonian for the second wave, right? The second the harmonic generated wave. So its frequency is 2 omega. And then you have A2. So here, A1, A2 are just creation annihilation operator that are defined the same way as we previously have, okay, for the E1 and E2. So now, this, okay, if you only have this, then what you're describing the system is that you're describing a cavity that has has light photon of omega and also have photon of 2 omega, and there's no interaction. Okay, so this part we also usually call this part h naught. It's like the original Hamiltonian without interaction. Okay, and then the next thing is that, okay, how is this interaction? How do you describe that? So this is, okay, something that you can kind of imagine what the Hamiltonian would look like. First of all, you have to keep the dimension the same, right? So whatever you have, it should have h bar. So this one is a little bit tricky. Sometimes people use capital omega. Okay, h bar capital omega, sometimes divided by 2, depending on the following calculation what will happen. So h bar omega, capital omega, which make the dimension the same as frequency. And then what you have, okay, here is that this process, what it says is that you generate 2 omega frequency. And then to generate that, because you need to keep the energy conserved, right? So you need to annihilate 2 photons of omega frequency, right? So annihilate 2 photons. annihilate 2 photons. And then the next step is that, okay, then this reverse process, should also be described in the Hamiltonian, which is 2 photon, well, 2 omega photon is annihilated to generate 2 photons at the frequency of omega. So that you can imagine, okay, this is the second one. Generated 2 photon at omega and then annihilate 1 photon at 2. Right. So, but the other thing that you need to keep in mind is that the Hamiltonian, okay, here is Hermitian. It means that if you do conjugate transpose of that, okay, or if you do complex conjugate, you can understand it in that way, then it has to return to itself, because the Hamiltonian is something that you can measure. It's just the energy of the system. So that when you do that, you need to keep your Hamiltonian Hermitian operator. So we have omega, then you have to have omega conjugate. Okay, and this is what we call the interaction Hamiltonian. Interaction Hamiltonian. Okay, interaction Hamiltonian. And people have studied this, for a really, really long time in quantum mechanics, because a lot of times, we don't really care about this part. This is just photon that go along without interacting. We're actually more interested in this part. So there are actually ways to only use interaction Hamiltonian. It's called interaction picture. And there's ways to do transformation of your wave function in Schrodinger equation, and then develop a series of equations only consider the interaction. Now, and of course, when you have the Hamiltonian, then you can go through all the quantum thing and then calculate it. So, but the point here, okay, I want to make here is that why would the Hamiltonian look like this? Okay, is there a connection between this Hamiltonian and the classical equation we use for the nonlinear optics? Okay, so to understand that, I want to make it relatively quick. Okay, so first, the classical case, what we have is this is come from the Schrodinger. Well, sorry. It's really interesting is that the in one of the qualifying exam, when we have a question of how do you simulate EM wave mode in a microcavity, in a photonic crystal microcavity, and then this is in a paper, right? This is how we do the qualifying exam, and then one student answers that using Schrodinger equation to simulate EM mode and EM field, and so of course you can imagine the result, but it's quite interesting, like to make sure that he meant what he meant. I actually asked him to write down what he meant by which Schrodinger equation he's referring to, and then I hope that he can write down. Maxwell equation. Okay, but unfortunately, he really wrote down Schrodinger equation, and I have no idea. Okay, how he would try to solve EM mode from there. Okay. Anyway. So this is the classical case. Right, you have light propagating here, and then the differential equation is on Z. The differential equation is on Z. Okay, and by solving this, then you can get the input-output relationship and know the electrical wave at every Z. Right. So here, to make our analysis simpler, one thing I want to do is I want to assume that we don't have phase matching problem. So it's phase matched all the time, so that the k will cancel each other. Okay, because phase matching is not related to quantum. It's just momentum conservation. It happens both in quantum and in classical case, so that we don't need to spend our time on that. Okay, and then after that, you see that the frequency term can also cancel each other, so you end up like this. Okay, so the classical case is actually quite straightforward. What you have, okay, is that you can reduce this type of equation into right. This is your first equation. Is that, well, there's an I. Okay, we need to keep the. So the differential on E1, okay, is proportional to E1 star and E2, right? And then also the differential on E2 is proportional to I, and then there's coefficient, right? And then E1 squared. Right, E1 squared. So what you would think, okay, is that because there's a connection, okay, in classical case, you use electrical field to describe the equation, and you try to solve for electrical field. And in quantum case, you use creation and annihilation operator. You try to, well, there are several ways you can do this, but one way is that you try to solve the evolution of these operators in interaction picture or in a Heisenberg picture, but you don't solve for the wave function. So, then there's a connection between A and E, right? Because previously we have defined what is, we have solved, okay, what is A and A dagger, okay, in terms of E, so that you can actually build a connection, okay, between the Hamiltonian here and then the electrical wave here, right? So if we assume, right, this is a traveling wave, not in a cavity. You can do the cavity as well, but here we assume is traveling wave. Then we know that E is equal to, okay, we just say generally E, okay, not 1 and 2, is Ex psi. This is the amplitude of vacuum state. Okay, and then plus okay, so if we do this, then one thing that we have to keep in mind is that when we are writing down the nonlinear Schrodinger equation, when we are writing down the nonlinear equation for electrical field, we are only writing down for the negative frequency components. So what we mean by E1, okay, this E1 is actually this part. It's actually this part, right? This part is actually E1. So that you know that, okay, eventually, if these two are kind of the same equation, if you can reduce, if there's a connection between quantum case and classical case, then the quantum case should give you an equation like this. We don't have Z, but we have T, right? Because in Schrodinger equation, we don't solve for position, we solve for time evolution. But this one is easy to build because position can be time times speed of light, right? So that you can easily convert Z to T, okay? And then proportional to A1 star, okay, this A2. And then another equation will be A2. Okay, and then A1. Right. So if from quantum picture you can derive equation like this, then what you can do is that, okay, you can make the comparison between classical electrical wave and quantum electrical wave, and then you say, okay, this part can be replaced by E1 if there's enough number of photons, right? You can replace the operator with a number, right? Then you can move from this equation back to your classical equation. So this is actually a very standard way of how to convert from quantum, the conversion between quantum and classic. Okay. Now let's take a quick look of how you can derive this type of equation in the quantum picture. So in the quantum picture, what people use, for example, here you can use interaction picture, or you can use Heisenberg picture. It's the same thing, okay? But the key concept here is that because these operators are extremely easy to use, so that we don't want to solve for psi t. Okay, we don't solve for this. Okay, this is typically what you would do in the quantum mechanics. You solve for evolution of wave function, but instead, what you do is you solve for the operator and their evolution of t, and then you say, okay, how eventually you want to know a little bit of the eventually when you try to measure something, right, you need to know the state. So what you do is here, this is the state, always stay in the initial condition, and then what is evolving, okay, with time is the operator instead of your state. And some people will say, okay, this is counterintuitive, but I want to use Heisenberg's argument. This is actually intuitive. And the reason is that, okay, think about this. If you want to measure position, if you want to keep track of the position of a particle, in quantum mechanics, what you do? Okay, what you do is that you write down the Hamiltonian, you solve the wave function, and then you calculate the expected value of a position operator, right? You don't keep track of the position itself, but you keep track of the wave. And that's actually not intuitive because, okay, I just want to know the position. Why do I have to calculate the wave function? So in this picture, okay, the interaction picture or the Heisenberg picture, what you have is that not tracking the wave function itself, but tracking the position operator. Okay, tracking the position operator, it's almost like return to the classical case where you measure the position all the time, right? Monitor the position, you measure the position. So this is in some sense, okay, more intuitive. But the argument here, okay, I want to make it very clear. These two are equivalent to each other, and to choose one, not the other, really depends on what system you're calculating. And then in some system, it's easier to calculate the evolution of wave function. In other system, it's easier to track the operator. Okay, let the operator evolve in time, but not the state. And in this case, in almost all the photonic case, it's tracking the operator here. Okay, so let's say in Heisenberg picture or interaction picture, Heisenberg picture. So a few simple things we can have is that if there's an operator A, then its time derivative is I h bar, the commutation between h and a. So when we write down this, we assume A does not have any time dependent as an operator itself, right? The operator itself doesn't have a time in it. For example, the position operator, right? When you write down position, it's x. When you write down momentum, right, it's right. There's no t or like t squared or partial t in your operator. If you have this, if you have all this, then you need to add another term here, the partial differential between a and t. Okay, so this is the Heisenberg picture if you have an operator, then how it evolves with time, okay, it's governed by this equation. And by looking at it, you'll see, okay, this is very, very nice, right? Because you calculate this and probably you will end up here, okay? Partial A1, partial T. Okay, this is A, T. And then now, so okay, so this is evolution of operator, but how do you use it, right? Suppose, let's say you want to measure the photon, right? The number of photon, or you want to measure the position operator X, which is A plus A dagger, right? Then how do you measure all this, right? And because we know that position operator represent one, let's see, position operator is actually one of the quadrature amplitude. Later we'll see that. Okay, suppose you want to do something like this, and then you want to measure it. How do you know you want to measure this? So how do you know its expected value? And the way to do it is that you do the inner product of your initial state, act on the operator X, that is with T, right? So the evolution of the operator is solved here, and then, okay, do the inner product of this. Okay, do the inner product of this, and if you find it difficult to understand or interpret, there's a relatively easy way to think about it in linear algebra, right? So suppose, okay, you want to calculate an operator's expected value, right? You want to calculate something's expected value, and in quantum mechanics, what you would do is the state, well, in Schrodinger, not picture, but in standard Schrodinger way, what you would do is that you solve for the time evolution of your state wave function, and then you do the inner product of your operator on this, and then it gives you the expected value. This is kind of like you can derive this from the definition, well, not from the definition, from the assumptions of quantum mechanics. So if you write down psi t, if you think, okay, this is true, if you think psi t is from evolution operator act on the initial state, right? It must come from the initial state, and then there's an evolution to evolve your state into into this state. Then if you accept this, okay, you can actually prove that this is true. This is actually okay. If you accept that, then your A can also be written down as psi 0 U dagger, right? Because your left bracket, so it's the conjugate transpose, and then A, and then U T, right? You can simply, okay, express this as this and plug it in. Then what you see is that, okay, this already looks extremely similar to what we have on this line, right? You have initial state as left and right bracket, and in the middle, okay, this part is actually your A, T. So what it is that, okay, your operator itself originally is not dependent on time because you put all the time evolution into the state. Okay, but if you assume that the state is not evolving, but the operator is evolving, then okay, then you have the evolution operator operator act on your state and make your state evolve with time. And this is actually very, very standard in linear algebra. It's like when you do a transformation, okay, if you do a certain transformation on time, on your basis, on your eigenbasis, then if the transformation is U, then all the matrix that defined in your linear space will have to go from a U dagger U transformation. And you can try to look for the this theorem in linear algebra. I think this is widely used in ECE, the when you process imaging. When you're processing data and you need a transformation of basis. Now, so let's take a look here, okay? And then so if we use this equation, right? If we use this equation, let's write it down as A1, right? dA1 dt equals to I divided by h bar. Okay, there's constant here, I divided by h bar, so h cancel each other, so you have omega here. I, and then you have need to calculate the commutation relation between A2, A1, okay, with A1, right, with A1. And then you have the second one is I, again I, right? Second term here. And then it's A1 dagger, A2, A1. Okay, so a very simple way to calculate this is that to use the commutation relationship. Okay, you have AI, AJ, whatever. Okay, this is delta IJ. Okay, if it's not the same frequency, if they're not the same frequency, they're not the same mode, then your commutation is always 0, which means you can, for example, this one, right? The commutation is on A1, so A2, whatever you have A2 commutation with A1 is always 0. If you have that, what it means is that you can treat A2 dagger as a number here, and then move it wherever you want, because whenever you move it, you switch the order between A1 and A2. It doesn't change anything, right? So you can treat this as a number. Okay, so in this case, A2 can go up and go in the front, and then this A2 can also go in the front. And the second thing that we have to remember is that an operator's commutation with itself is always 0, right? So a square is a square, and it doesn't change no matter what you do, right? So this one is so this can help us to simplify this commutation calculation. First one, this one doesn't matter. You can move it to the front. It doesn't change your result at all. And then your commutation is A1 with A1, and no matter how you can calculate it, A1 is always 0. So this is 0. Okay, so we need to calculate this one. Let's say A1 dagger A1. So this term, let's modify a little bit to make it easier. So what we want to do is that, because A2 has nothing to do with A1, right? So you can move A2 as a number in the front. Okay, A1 dagger, A1 dagger, A1. Okay, so all you need to do is to calculate this. And the way to do this is fairly straightforward. Let's see if we can finish in this. So you just write it down by definition: A1 dagger, A1 dagger, A1 minus A1, A1 dagger, A1 dagger. Right? And the thought now here is that you want to make these two terms look almost the same so that you can cancel something. And there's really only one relationship you can use, right? It's A dagger equals to 1 plus the commutation relationship, right? A dagger A. Okay, A dagger A. So what you can do is that you can use here sorry, what you can do is that you can use this one. You have AA dagger, right? AA dagger, so that they become minus 1. Okay, first 1 plus A dagger, so this A1 dagger, and then minus 1, minus this part, A dagger, A1 dagger, right? And then what you can do is you can do next is that, okay, you see there's another A1 dagger, right? You want to get rid of this, and then this is minus A1 dagger. When you change this, you again have a 1, so you have minus A1 dagger. And then this thing times with A1, so A1 dagger, A1 dagger, A1. And what is in this dot dot dot, right? In this dot dot dot, it's just A1 dagger, A1 dagger, A1. Right, so you see that by doing this, okay, you cancel out this term and this term, and you'll end up with minus 2 A1 dagger. Okay, minus 2 A1 dagger. So here you will have equals to minus 2 I omega star. Okay, and then A2 A1 dagger. Now, if you look at this equation, okay, this is exactly what we have predict, right? So this evolution, okay, this evolution of time has to be A1 dagger and A2, so that when you, if you write down your electrical field of the light like this, and you can say, okay, if I want to return to classical case, I replace this with a vector E1 and E2, then you will return to the equation like this here, right? E1 star is just A1 dagger, E2 is just A2. Okay, so you can do the same thing for operator A2, okay, to see that, okay, this equation is actually the same. And notice a factor of 2 here. This is exactly the reason why in a lot of cases, when you see when you read textbooks or papers, people actually have a a factor of 2 here, factor of 2 here. And then another thing is that, okay, this in this case the I, okay, the complex number really doesn't matter that much, because the reason is we always have a degree of freedom to choose our frame. For example, if this process is something called degenerate parametric oscillation, which means that E2 is a pump. Okay, E2 is a pump. Then E2 is a pump. Then what we mean is that, okay, there's actually a phase here, phase term here. Okay. The initial phase, you can think about initial phase as choosing the 0 time. Okay, choosing the 0 time in your frame. Then you can always choose the initial phase to change this I, okay, from I to a real number. For example, you can add 90 degrees in the phase, then A2 will have a term of I and cancel this one. Okay, and so the factor I here really doesn't matter that much. The only important thing is that make sure that whatever you do, okay, your Hamiltonian turns out to be Hermitian, right? It's the complex conjugate, or the conjugate transpose of the Hamiltonian always return to itself. Okay, so this is how we make this connection. And the next part, what I would do is that I would show you guys this special case of degenerate parametric amplification. Okay, degenerate amplification, and show that, okay, there's something interesting in the quantum sense. Okay. Now let's come to using this quantum picture to calculate one interesting situation in nonlinear optics, which is actually well started since 1970s, and then this is exactly, well, what we are calculating here is exactly what was put into LIGO, the gravitational wave detector, to generate something called squeezing state to make the LIGO more sensitive to small signals. So the situation we're considering here is what we called degenerate parametric amplification. Right. The thought is that, okay, you have a photon that come in as 2 omega frequency, right? And because we know there's a chi2, right? So there's a process that you can split this photon and then generate 2 photons of h bar omega at the same time, right? So if we write down the Hamiltonian of this, is that, okay, you annihilate 1 photon and create 2 photons here. And the other way is that you can, well, of course, the reverse process will also happen, so that you have 2 photons, okay, annihilated and create 1 photon here. So here what you can think of is there's a classical pump of E2. Okay, E2 is can be considered classic in this sense. It's a very strong pump. Okay, so later what we will do is we'll show that you can reduce A2 and A2 dagger into a number. Okay. Now, so the thing why we're considering this case, there's very deep, there's very deep interpretation of that based on the Hamiltonian. Okay, whenever you see A1 together, A1 dagger together, there's something interesting. But here I want to use a very intuitive argument here, is that think about it think about the correlation here. Okay, these 2 photons, they're actually dependent on each other, right? There's no way that you can have a 2 omega photon come in and only generate 1 of the photon, 1 h bar omega photon, because that would violate the conservation of energy. So that if you have this photon, then you must have this photon. They have a correlation that was built because of energy conservation. And also because of quantum mechanics, everything is quantized, so that you have to generate 2 of them, okay, simultaneously. And because of this correlation, there are 2 ways you can understand this. One is that there is a special entanglement here. Entanglement means that when you're doing the measurement, if something happened here, then you can predict the result here, right? So what happened, okay, if you're verifying entanglement, then what you do is you put a photo detector here, okay? If often, okay, in doing this experiment, often that what you do is that you match the phase matching conditions so that these 2 photons would have a slight angle, right? So that one come here or the other go there, you can separate them. Or you choose, okay, these 2 photons can be in different polarization, and later you can use a polarization splitter to separate them in your measurement. So if that's the case, okay, then the entanglement is usually verified by adding a detector here, a single photon detector here. And then, okay, for most of the time, okay, there's the 2 photon ray doesn't, the 2 omega photon ray doesn't generate these pairs of photons, then your detector doesn't have a dark current, it doesn't show you any photon. But whenever you have a photon arrive here and then light up your detector, you're 100% sure, if your experiment is well designed and well prepared, then you're 100% sure that there will be a second photon. Okay, the other photon is also generated and arrive at this detector. So this is called entanglement. It's either entanglement is written as, okay, it's either no photon at both paths, or both have 1 photon. Right, this is the state of entanglement. Then either both of them no photon or both of them have a photon. Okay, and of course the coefficient will be slightly different here, but this is the best case for entanglement. So this is one way to think about the system. Why is it different from classical case? Okay, because the photons have to be generated at the same simultaneously. They depend on each other. There's a correlation. And the second part is okay, if there's a correlation, think about it. and this correlation is mandated by energy conservation, then maybe there's a quantity, okay, there's a quantity that, for example, one thing minus another thing represent this correlation, and this quantity might approach zero because their correlation is mandated by energy conservation. So that is what we're going to look for. That is actually, there's a name for that, it's called squeezing. And the concept is that, okay, we use in a normalized XMP, which means XMP has a dimension of 1, then this is, see, there's a different way of writing this. Okay, let's see, if greater than 1/4, right? Then individual of them, for example, the Gaussian state, well, not Gaussian state, for example, and if a state that's symmetric, then you should have each one of them to be 1/2. Okay, each one of them to be 1/2, so that your position and then your momentum are equally weighted, which make a lot of sense, right? Because we write down Hamiltonian, the momentum represent kinetic energy, the position represent potential energy, and then they are indeed equally weighted. So this is, the case if you have so this is the case that sets your minimum uncertainty, right? Because their product has to be larger than 1/4, and then if they're equally weighted, then the minimum they can be is 1/2, right? 1/2 on each of them. So the idea is that, okay, if you now have the photons have a correlation, they're generated together. Is it possible? Okay, is it possible to find an operator? Let's say find an operator, and then also normalized, and then its uncertainty can be smaller than 1/2, can be smaller than the minimum that's required here. And of course there should be a penalty, right? Because we know the uncertainty principle, you cannot break that. So there's a penalty that if you decrease one of the uncertainty, then you have to increase another quantity's uncertainty to satisfy the uncertainty principle. So this is the basic idea, okay? We look at the case that might be interesting in quantum wave, and then we look for something that we could say useful or interesting to calculate with this. So now what we do first is that because the input light is a pump, it's a classical wave, it's a pump, it has many photons. There's really no reason to write it down as A2 dagger A2. Well, it really doesn't have to be A2 dagger A2. The reason is this. Okay, think about what this operator would do when you act it on a state, right? A2 has to act on let's say A2 act on a state of 2. Right, the electrical field of E2, well, the state of the corresponding to 2 omega frequency, okay, labeled 2 here, has n photon, right? And then what you would do is that you will have square root of n minus 1 to photon. Okay, so you reduce the photon number by 1. Now, if the photon number is very large, it's a classical laser field, it has billions of photons, it really doesn't make much difference. You can actually compare the photon state. It actually doesn't make much difference when you reduce from n to n minus 1. Okay, it really doesn't make much difference. So this way, okay, what you would do is that you can say A2 can be reduced to a number alpha 2. Or I think in many cases people just write it down as alpha because that's the only number, okay, you have. And then A2 conjugate goes to alpha conjugate. Okay, So the reason is that, okay, we've explained here, the reason is that well, this is the same assumption as non-depletion assumption, is that you assume that nothing will happen to the pump laser, okay, and in this case, it's actually true, okay. So if you do that, okay, you can replace A2 dagger and A2 operator and A2 dagger operator into numbers, and now so you have, and then you plug in the equation of motion for the interaction picture. Then what you get is this dA1 dt. Okay, so you have a coupled equation for A1 and A1 dagger. So here, one thing that you notice that, okay, is that alpha is the electrical field, right? The input of the field. And we know that, okay, if you have an input of the field, you can actually select the phase, right? You can select the phase here to make it a real number, imaginary number, or whatever number you want to make it. So here, what I want to do here is that I don't want to carry the I here, right? It's complicated when you calculate things. You have to worry about I squared is -1, right? So I don't want to carry this. So what I can do is I can redefine alpha to get rid of I. Okay, so I define alpha, definition of alpha, I define it as, right, a constant. It has a phase, but I want to multiply with I. Okay, I, a magnitude, amplitude, and then a phase, right? So what it is that I assume there's a pi/2 phase on here, and then I bring the I here. So that when I plug in this into here, you can see that I will cancel this I. Okay, I will cancel this I. So you get dA1 dt equals to G alpha EI phi A1 dagger dA1 dagger dt okay. So we reduce to this, and these two equations are really equivalent to each other. You're just selecting the phase, and you can even do one step further. Okay, many textbook doesn't do that, but here we want to save time. Right, we can assume that the phase is 0. Right, then you arrive at here. Let's rewrite it a little bit. Okay, so here you might think, okay, the standard way to solve this is that you take the derivative of t on this, and then you plug this in, and you get rid of A1 dagger. And then you can solve what A1 is, what A1 dagger is. Here I have a simpler way to do this. Okay, I have a simpler way to do this. Is to recall the definition of x and p, right? The position operator and momentum operator. So when we define when we quantize our electrical field, we see that the definition of A, okay, is x plus IP, right? And then A dagger is x minus IP. At the time, we didn't use x, we used q, right? It's the same thing. So if you have this, then you can add these two equations together, minus these two equations. And what you have is x equals to A plus A dagger divided by 2. P equals to A minus A dagger divided by 2I. Okay, so x and p by A and A dagger. So if you look at this equation, there's actually a very simple thing you can do, is that you can add these two equations together, right? then the left hand side will be A1 plus A1 dagger. Right hand side is also A1 plus A1 dagger, right? So you create an equation for X, and it's a very simple equation. And you can do the same thing as equation 1 minus equation 2. Then you create an equation for P, right? So if you do that, then this transfer to A1 plus A2 and then divided by 2, right? So you get, let's see, I didn't write it down here, but dx dt, right, plus together and divided by 2 equals to g alpha x, right, because this side also is, add together is also x. And then the other one is this divided by that and then divided by 2i, right, so you can have dp dt. And this is critical here. Okay, notice that if you minus this 2, this side is A1 minus A1 dagger. This side is A1 dagger minus A1. So you acquire minus sign phase. Minus sign here. Okay, so it's look like this. So this one is extremely simple to solve now, right? Because this is just exponential solution. Xt equals to E g alpha t x0, and p would be pt would be exponential minus g alpha t p. Okay, tp. Now we can take a look at this equation here. Okay, so if we were to calculate uncertainty value of these two equations of x and p, okay, at different time, then what you will see is that so first of all, for the initial state, okay, here what you would do is that you take it as vacuum state, right? Because initially your light is here, so there's really no photon is generated, so it's really a vacuum state at h bar omega frequency, right? So initially it's a vacuum state, and then you satisfy the minimum, the vacuum state satisfies the minimum uncertainty principle. Each one of them is 1/2 in the normalized dimension. Okay, and as the time evolves, okay, you still try to calculate this, right? And when you calculate this, you just acquire a number, right? You simply acquire a number when you calculate the expected value of x and p, right? You don't change because the operator itself is the same as for the vacuum state. So what it would do is that it will have delta x squared is equal to, okay, e to the 2g alpha t, okay, delta x 0, and then delta p will equal to 2. Right, so you just plug it in, and then you pull out the number, and then you notice that at time t, okay, it's actually the same uncertainty, but you multiply a factor. Here is the same multiplier factor, and this factor is larger than 0. Oh, sorry, larger than 1. This factor is smaller than 1. Okay, when you multiply delta x and delta p together, this factor gets cancelled out, and then you return to 1/4. So what it means is that if this is smaller than 1, it means that the uncertainty of momentum operator gets suppressed. Okay, so momentum is has less uncertainty in it, so you know a little bit more about your momentum. As a consequence, you will know, you see that the position operator uncertainty goes up. Okay, goes up exactly, how much you go down, it goes up the same amount. And so that you will have less uncertainty, okay, in your, you have actually more uncertainty on your position operator, okay. And so this one is very easy to solve, and then this is actually called squeezing, okay, squeezing of the operator so that the your uncertainty level deviate from the 1/2 the ideal minimum. Okay, and okay, so if this is squeezing, then the next question we have is, okay, what exactly is squeezed? Okay, can we measure that, right? Because we're in a very abstract idea of A and A dagger, now X and P, position and momentum operator. So what exactly is this momentum operator that gets squeezed? So, so to do that, okay, what we have is to look back to our definition of electrical wave. Okay, so you have, so the way, okay, we want to do is I want to construct P, okay, A minus A dagger, that is your P, A minus A dagger. So, so then, okay, A is here, A dagger is here. To do that, you have to, probably expand these two terms so that you can collect the terms with the same, collect the term, with the same coefficients, so to construct A, X and P. To do that, then you can use e to the I omega t plus IKR, okay, is equal to cosine. You use cosine sine expansion, right? Cosine omega t minus KR plus I, actually minus I, yeah, because you have minus omega t, right? So it's minus I sine omega t minus KR. Right, you have this, and then you can also do the same for the conjugate. And because it's the conjugate, you know that this is just a conjugate. So you only change the sign from minus I to plus I. Okay, so that you plug that into E, your your equation, well, your electrical field. Okay, and then what you have is you have A times this exponential, so it's cosine minus I sine. So A cosine minus I A sine. Right, this is, you can omit, we can drop whatever in the middle here, and then in the bracket here, and then later put it back. And then we have A dagger. A dagger is cosine plus I sine, right? So plus A dagger cosine plus A dagger A dagger sine, right? So that this one, you can now collect A and A dagger together. So it's E epsilon A dagger. So you have, let's put a 2 here. Okay, so you have A plus A dagger divided by 2. Okay, because we put a 2 here, and then cosine omega t minus KR. Okay, cosine. And then here you have I, right? So it's minus I A minus A dagger divided by 2 sine omega t minus KR. Okay, so so now if you look at this, then this part is X, right? By definition, this is X in a dimensionless form. Okay, this is X. And then here, okay, you need to change a little bit because P is divided by I. So you put I here. Then what you do is you multiply I both here and here. I is equal to 1, minus 1, so this one is. Okay, so this is your P. So this is something I think you guys have learned in your engineering class, right? This is called quadrature amplitude. It's that you have a wave, and then you can decompose it into cosine and sine, which means one wave is 90 degree behind the other wave in terms of phase. Okay, so cosine and sine, and then this is called quadrature amplitude, right? So it's like for the cosine wave, the amplitude is described by operator x. And for the sine wave, the quadrature is expressed by operator p. Okay, and if you want to measure x and p, then the easiest thing you can do is that this is the same as how you get the quadrature amplitude, right? You can beat this E, okay, you have a E wave here, and then with another wave, local oscillator, homodyne detection, okay? And if this wave is in phase with cosine, right, then you can do the integration, and you know that when you arrive at the detector, and because detector only have a limited response bandwidth, right, so you need to do integration between E and E prime, then what you will see is that, okay, then if it's in phase with cosine, right, then you have a cosine square term, then this term, sustain, and then you have x, and cosine and sine, they're off phase, and cosine and sine, you can do the integration, it's always 0, right, so you drop the p term, so so in that way, okay, by controlling the phase of this local oscillator, you can choose this local oscillator to integrate cosine or to integrate sine, okay, on your detector. So the output would be proportional to either x or p, okay, depending on what phase you choose, okay. And this is actually the how people apply this. Well, this is exactly how people use in LIGO, is that you generate a squeezing, and then you turn your local oscillator, well, the very powerful laser, in phase with the P, okay, in phase with this sine, and then when they arrive at the detector, okay, the noise is actually dropped by this P factor here, the squeezing factor here, and then so that you can have the noise floor, okay, the noise floor is determined by this uncertainty delta P. So the quantum limited noise floor, okay, this is quantum limited noise floor, will drop so that allow you to see smaller signals and then be more sensitive to, have your detector be more sensitive. And this only applies, okay, let me say this only applies if your noise is dominated by quantum noise, okay? If your noise is dominated by a truck driving next to the detector and then the vibration causing the noise, then you wouldn't see any improvement, okay? It has to be, you have to first see the quantum noise limiting your measurement, and then apply this squeezing technique to improve your sensitivity. And so this is why, okay, I remember the variation of this in LIGO was done somewhere around 2010 or 11, and then but LIGO was built, okay, since 1970s or 1980s, so that it actually took a long time for them to see the quantum noise at a certain wavelength, well, not wavelength, at certain bandwidth they want, certain frequency they want, and then to really suppress that with a quantum technology that was developed since 1970s. Okay, and that is all for today. And then I will actually add another lecture describing the full quantum picture here, because if you think about it, previously, okay, here we still use, okay, nonlinear optics, right? H bar G. We treat the material, okay, chi2 material here, as a classical material, as a coefficient chi2. And in deriving this chi2, what we do is that we treat the material as quantum, right? It has many energy state, but we treat the light as classical light. There's a E wave there. Okay, so we haven't got in a case where we treat both the EM wave and the material as quantum. Okay, what we mean is that for the wave, EM wave, you have to quantize it as A and A dagger. And for the material, you have to have separate energy level. So only in that case, we call it a full quantum model.